Okay, great, thanks. So now I'm going to present two small projects that we've been doing. These were year-long projects, but because of some personal delays, they've been extended. So they're both sort of in the halfway phase. So they're work in progress. And then hopefully next year we'll have the final results. And these are a little bit forward thinking in some ways. So they're related, of course, to industry always and regional materials, but we're trying to think a little bit in the future, but still here. So the first one is called, Next Generation Flat Pack Deployable Wood Building Components. And this project picks up on a lot of the work that we've done or that I've done before as part of my PhD. But we've also been super lucky to integrate now a new team of UO students and at the graduate and undergraduate level that have particularly been interested in working in this area, which is really fun. The basic idea for this work, if you don't know my previous work, is that we take the hygroscopic and hygromorphic properties in wood, which means that it shrinks when it dries out and it expands when it gets wet. And we try to employ these in multi-layer wood systems as a method of self-shaping. So normally this would induce problematic changes in shape when wood dries. I guess you all know that, right? And it's seen as a defect. And here what we do is that we use computation and a bit of classic design skills in order to implement this as a functionality. And this we've done this on a building scale in Europe with Bloomer Lehman. And have implemented it for CLT in the factory. But the easiest way to explain it is with this furniture, which is also from a company that I started as a spinoff. But basically that you can get a flat pack piece of wood. It has the makeup is programmed physically in a certain arrangement, so not exactly like plywood. And it has a higher moisture content. And then when you open up the package in your house over a day, in this case, it shapes out autonomously without any machines or mechanics or plugging it in or anything like that. Also no instructions. So I mean, think about the master, we talked about on-site robotics, but what if the building just shaped without even plugging it in? I mean, that would be pretty spectacular. So that's sort of a bit of the background. And then of course, I'll show you the promotional video of how this works. You get it, you open it up. It doesn't spring up, which is good, right? So you just let it there and I don't know, let your cat run around and see it. Or I think a Fast Company editor said how many bottles of wine could you drink in a party if well it shapes because everyone thinks it's bad that it's slow, but maybe it's nice with everything moving so quickly. So that's the basic concept. But of course, we do buildings, and what I was really interested in when I came here is the next stage of this is we can do fancy buildings, but could we actually do products that take this principle and really work structurally? So in the proposal, we proposed something like this, which was that one, we wanted to test it out with Ferrous veneer because we can get it here, and also the peeling is more efficient than the sawing, and we use relatively thin layers. So we thought this would be really fun. One, see if we can use veneer instead of solid boards. And then two, could we really think about this as a product? So we started looking at it in the proposal like a slab. I presented this last year. And seeing, okay, could we just modify the buildup a little bit? So we almost build a plywood, but with special buildup in some of the layers, and then have these ribs deploy hygroscopically on site. And we've started doing that. And of course, the advantage of that is okay, could one stack of plywood make a whole bunch of ribbed volumetric components really efficiently, and then we could put more of them on the truck. So we've started work with that, basically measuring some of these properties in a very low-tech way, but still technically valid way to understand the expansion coefficients, with the regional veneer, and then the curvature that this creates. And we've done some validation tests, and we're still working on that in order to get to the slab. And then in parallel, we also started working through two different student projects on another idea, which was what if we could actually not do a slab, but do tubes or cylindrical components. So if we're going to use curvature, why don't we just use it all the way around? And then we can make these components even thinner. So this is some work from the students. Let's see if it will play. So again, and you can ask you can ask the students and after like how many tubes we can fit on one truck. It's spectacular. But like basic idea, you go from a flat sheet to a curved tube, and then you can pack it all in like super efficiently. And it's shocking like how many tubes you can fit in a truck. And thinking about this in a sort of quasi-manufacturing, that we're peeling everything off and then just like relayering it. So like even if we didn't use the deployability, it's like we can get 100 tubes out of one log, right? So it's like we're peeling it and then like repeeling it. And if you know like pole barns or telephone poles, right? I mean, the question that then we come to is like, how many times do we have to wrap it around? And it probably is definitely doesn't need to be solid, right? So I think it's a pretty convincing concept. And what some of the students worked on this summer was looking at the variability in the diameter that we get, because the natural variation in the material has a big impact in the shaping. And then also preparing samples. This is the fun part. Where we prepare flat and then they curve up. You can see there's variability. You also see like sometimes they like crack themselves, which isn't good. But we're working on that. And what we did is we prepare a whole bunch of samples, and then we crush them, also with assistance from Erica Fisher from College of Engineering. We're crushing them in like a standard compression test to start with. And then we also looked at, so wait, hold on, I have to play the video. Let's see. This is like fun for architects, but maybe normal for engineers. And it's like pretty, oh, it didn't finish. Uh-oh. Okay, we'll show it in the tour. So like, but what's crazy is that these are also so lightweight, right? So of course, like they can't take as much compression as like a solid steel or concrete or a steel tube, but compared with the weight, it's like crazy how much force they can take. These are some of the like early results. We haven't published this yet. And then we also worked on upscaling. So what's really cool is that this can actually upscale. So we switched from a, let's say, not regionally sourced hardwood veneer to using the Ferrous veneer, and we get these green from the factory. So there's also no energy used in the kiln drying, because we're converting that normally energy intensive step into the shaping process, which is like amazing. If you want to talk about LCA, like that's great. And then we were able to successfully do this on a larger scale. And we measure the weight and of course the geometry over time and stuff like that, using the 2 layers of 1/8" Douglas fir veneer, as well as still a thin maple veneer around the edge. And it's like shocking. It almost like works better on bigger scale than smaller. And of course, people also always ask like, okay, but then you need to have a climate chamber or whatever. We also tested it in the great dry conditions of the Oregon summer with even better success. So we started this like too late in the day, but I'm quite sure it will curl up in one day in the summer, which is really cool. And maybe another thing is that the process is reversible. So we don't have a swimming pool big enough yet to put the big tubes in, but we've shown it with bathtub that it can be reversed. And just like a little bit like about the results of this and where we're going, we've done more compression tests, and then we're going to share the initial results at the World Conference for Timber Engineering, WTCE in Brisbane in June. And we're pretty excited about what type of structure we might build next. This project is also partially funded or mostly funded by the ARS program as well, and nicely supported by the College of Design from the Dean's Office with a research grant, as well as from Ferris. Okay, and then the next project is a little bit more serious. So this one I'm presenting on behalf of a team in the College of Engineering. So myself, Dr. Erica Fisher, and also Sebastian, who's a PhD student in Erica's team. He's here in the back. So you can direct your technical questions to Sebastian. This is also really nice because it's the first time that we've worked with structural engineers here. And it's been quite fun so far. So like this also comes out of this idea that, okay, we have mass timber, this is from Lever, great architecture. But like there's a sort of like thing that issue I have here is that like we're always using these flat panels, and I guess like that's the first step, right? But we also know from like history that flat and mathematics that flat panels are not necessarily always the most structurally efficient. So this is from an architecture book, right? That if we curve up the piece of paper, it can span further with less material. And this is also something that we see now with other types of material systems that are maybe even more challenged than us in mass timber in order to use geometry or use other methods in order to optimize the material use. So I think this is super interesting that now concrete is optimizing. They are really optimizing because they need to get less material. And in mass timber, we are like definitely still in the stage of like using a lot and like maybe considering optimizing in 15 years. But I think we can learn. I presented this also in a conference with a lot of concrete people. And like, I think we can learn a lot from that why don't we just jump the gun and start optimizing now, right? So this is like hugely popular now to build these to go back to these vaulted, they're called Kappendecke systems, Gustavana vaults, like it depends where you go. Really popular historically, where you use a little bit of curvature and you get a lot out of it. Also with bio-based materials, there are some groups now working like around the world in these types, like how you can use these geometries in order to like add to what the material can do structurally, right? And it's not a lot. We don't need like crazy geometry, but I think it's really valuable, and I think we need to get going in this area. In my previous work, also, this is a bit more like special geometry, but we have done like optimization of how to use this curvature in like specialty structures. So this is like a corrugated shell structure. It doesn't really fit into categories, but here, like again, a small amount of curvature stiffens out this structure so that you can build it, I don't know, 14 meters tall with like really minimal amount of thickness. And this also has like architectural benefits, right? These are really cool. This is a new project that my team worked on in Stuttgart, in Switzerland, and in southern Germany. And of course, we've done these more like pavilion type projects. But in this project, with Erica and Sebastian, we try to break this down and make it a little bit more real, and also try to figure out why people aren't doing this yet, right? So we can break down those barriers. So the first task, which is mostly what I'll talk about today, is like how we can use single curved vaults and how we can figure out with timber material properties, like what curvature we would want to get and what the main benefits are. So we can't just take that. They might look like the concrete structure, but it won't be the same in the end because we're using timber. And we set up these experiments. This is all done digitally, where we're looking here. We started with a point support situation. And then we generate the models in Grasshopper, or the geometry on the architecture side, and then we pass them through a Python script that Sebastian developed in order to analyze them, of course, with the material properties and with different plies tested in Abacus using Python. And then we can set this up this whole system to run in different types of optimization loops, depending on what it is that we're looking for. And here we really set up the methodology, so we don't have like huge results yet, but then we will test it out and of course publish the results. What's really interesting is that when we set up the system, then we can also think about multi-objective performances. So of course we'll never get everything in there, but here we have the service level, the structural performance, and the material efficiency. And we have to consider all of these at the same time in order to get a good result. And that's what the computer can, of course, do very, very well. We use that in a confined situation. And then, of course, we can see which configurations perform better, where curvature is really working and where it maybe is just adding more material because the arc gets longer. And we can also figure out like how low we can go in terms of the amount of plies. So we won't really go into this like in a lot of detail, but in general, what we can see through this, or we can start to prove, is that the curvature adds potentially to the span that we can get, especially in a point supported situation. And even if we have to add material because the arc gets bigger, the structural benefit like outweighs that. And this we also presented really recently in Zurich at the Symposium for shell and spatial structures, which is a niche thing, but a big thing in Zurich. And we also will have an abstract at the World Conference for Timber Engineering. And looking at like where we're going, we've like done task one. We're going to refine task one based on feedback that we got from colleagues in the UK and in Austria that are working in a similar area. And then we're also going to think about how we can implement that more in a modular system in more reality. So tapping in a bit to the project that Erica shared virtually earlier about the floor slabs, we're going to try to like tap into that knowledge to try to push this one also further. Then we'll also look at another system that's maybe more used for a roof, where we have like more complex geometry of surfaces intersecting with each other, so that we can even get beyond the span of like a single component. And in terms of like, the next steps, we also are thinking about a way of adding acoustic analysis into the system, because of course these arches can have positive acoustic effects. If anyone knows how to do that in a very simple way, you can also chat with Braden and I. That would be great. And as well, we've seen like that there are some potential architecture projects or architecture leads that are really interested in this. Unfortunately, not yet in the Pacific Northwest, but we're definitely like sort of on that we're trying to push it both in the engineering and architecture level. And this one is, of course, also sponsored by USDA and Agricultural Research Services. And we're like working now on completing those tasks and then seeing about a further grant that we're thinking about for applying for actually validating the results like with physical testing. Thanks a lot.
All right, thank you, Dylan. So our last presenter in the design innovation session will be Judith Shine from the University of Oregon. So please welcome her to the stage.
Let's bring that down.